Good morning, everyone, and thank you very much for the introduction. My name is Lorenzo Saino, and I'm a software engineer at Fastly. Today, I would like to talk to you about health checking, in particular about a distributed health checking system that we built at Fastly to accurately and timely identify the health of specific services running on our infrastructure. Before starting, I would like to give you a bit of context. So, as I said, I work at Fastly. Fastly is an edge cloud, which is a bit of a fancy name for a content delivery network which provides some additional services, such as load balancing, image optimization, video packaging on demand, and many other services. You may have not heard of us, but certainly your browser has. We have a number of high-traffic customers that uses our services across a number of various industries. So we operate a globally distributed network of data centers, also referred to as points of presence, or POP in short. And whenever an end user makes a request for some services of our customer, we use a combination of IP Anycast and DNS redirect to redirect the request to the geographically closest points of presence, or POP. So for example, in this case, we may want to land in one of our POPs in San Jose or Palo Alto. Whenever a request gets into one of our POPs, it hits a number of possible endpoints. So in our POPs, we got one or more racks, and each rack comprises two different types of equipment. We got a stateless load balancer, which is the first point of contact for any traffic that comes into our infrastructure. And we get a set of hosts, and each host runs an instance of a reverse HTTP proxy, which we use to serve traffic on behalf of our customers. So, as I said, when traffic comes in, it first hits one of our load balancer. And then our load balancer has got a visibility on what service instances are up and running and are healthy, and then hashes incoming requests into one of the healthy servers. So as new request comes in, get hashed to different services. By the way, if you're interested in the design and implementation of our load balancer, we published a paper that will be presented in 2 weeks' time at USENIX and SDI 2018. So if you're interested in knowing more about the way we load balance incoming traffic, please, I would encourage you checking the paper. So our POPs, and actually POPs of all edge clouds and content delivery networks, have got some peculiar operational constraints. The first constraint is that space and powers normally come at a premium. And that required us to make some very careful consideration in the way we selected hardware and we designed our POPs. So for example, we do not use routers. We use switches instead, which have a smaller space and power footprint, but we had to come out with some clever way to still have a full routing table despite the limited memory availability on switches. Also, we don't use hardware load balancers. Instead, we came out with an idea to build our load balancer on commodity switches, which makes it possible to have graceful failover without the additional space and power required by hardware load balancers. Another interesting constraint is that we have a limited scalability. We don't have the luxury of being able to scale our POPs just spinning new containers on new virtual machine. For us, scaling a POP means a data center infrastructure engineer going on site and racking new servers. So whenever a POP is experiencing high load, the only chance we have to deal with it is to shed some load to neighboring POPs. Now, a fundamental component to effectively address this limitation is health checking. We need to ensure that we are able to timely and accurately identify the health of each services using a sophisticated mechanism of health checking. So we need to check the health of services timely, because if a service is misbehaving, we want to be able to identify that as soon as possible and remove it from production, because otherwise our end user will observe that. But at the same time, we want to ensure that we don't remove from production service unnecessarily when they're healthy, especially if you're experiencing high load. In fact, if you experience high load and we remove unnecessarily healthy hosts, we'll cause other hosts to actually get even more load. And that can actually have catastrophic consequences. We may even cause a cascading failure if we remove unnecessarily services from production while you're experiencing high load. Let me describe you a bit how typically health checking is done in normal infrastructures. So we got our cluster of services running behind the load balancer. And in each host, we got a number of components. So first of all, we got the service instance that we are actually health checking, which can be, for example, an HTTP server, a DNS server, It can be, for example, in our case, an HTTP reverse proxy. We then have a component which actually checks the health of this service instance. This can be, for example, a daemon running in the background, or can be a cron job, and checks the various types of metrics. For example, it can check if a process is running, if the CPU and memory utilization are within a certain safety threshold, if the response time or the error rate of the service instance is below a certain threshold, and so on. And then we also need a component which takes the results of this health check and does something with it. So it may, for example, want to page someone, preferably not, or report it to a monitoring system. But most frequently, what happens is that this component monitors changes in the state of the health of some services and signals this to the load balancer, so that the load balancer can make the decision to remove traffic from the unhealthy instance and fail over other healthy instances. I would argue that the process of distributing the results of health checks is very well understood nowadays, and there are a number of tools and techniques that can be used to address this problem quite satisfactorily. However, I would argue that historically, the process of actually determining the health of services had not received substantial attention. There is a typical assumption that it is sufficient in order to correctly identify the health of a specific service instance to look at the service instance in isolation. So I think that the vast majority of systems makes this assumption, assuming that just looking at one single instance in isolation provides enough information to make a decision about its health. However, I would argue here that there are certain cases where this is not sufficient. And to make accurate and timely decisions about the health of a specific service instance, we should not look at an instance in isolation, but we should compare it to other instances in the cluster and remove a machine from production only if its behavior deviates significantly from the behavior of the other machines within the cluster. Let me try to motivate this claim with a couple of examples. I'd like to start with an example whereby checking the health of a specific service instance in isolation is sufficient to give accurate results. Let's assume that we got a host which at certain points starts misbehaving because of maybe a hardware or a software fault. It will start failing health checks, the load balancer will be notified, and will fail over traffic over all other healthy hosts. Let me show you a production example of this happening. On the y-axis, I will show you the response time of an HTTP reverse proxy in our infrastructure over a period of T seconds of time. So as you can see from this graph, most instances are behaving pretty well, so they have a response time which is near 0. But there is one service instance which at a certain point starts misbehaving and is subject to an increased response time. This specific example, this was caused by a canary that was misbehaving, and they were responding poorly to an increase in traffic load. Now, identifying and correcting a situation like that is very simple. For example, we could define a health check to remove all the machines that experience a response time above a certain threshold, and that would have addressed this case quite satisfactorily. We would have removed the instance for production as soon as the latency increases above 25 milliseconds, and put it back into production after this issue disappeared. Let me show you a case, though, where this is not going to work fine. Let's assume that our cluster is experiencing high load, so all machines are pretty much experiencing a slower response time. Even if we have a very good degree of load balancing, so traffic is very equally spread across machines, we always have some machines which are experiencing a higher load, because there may be some little defects in the load balancing, or maybe it's running some background tasks that increase the load. At a certain point, we'll experience the machine experiencing the highest load to start failing health checks. This will result in the load balancer removing traffic and fail over to other machines. But then remember, all machines are already experiencing high load. So if you carry more load on already highly loaded machines, other machines will start failing, which then will cause traffic to be shared with other healthy machine, which will start failing health checks, and so on, until all machines start failing and you cause a nice cascading failure, which is something that we would really like to avoid. Let me show you an example where this can actually happen. Again, this is the same situation I showed before. I will show the response time of an HTTP reverse proxy over a period of time. And as you can see in this case, the response time is pretty much all over the place because all the machines are pretty heavily loaded. If you use the same health checking mechanism that I showed in the previous slide, which is removing from production machines which are experiencing high load, would have caused a very nice cascading failure because we would have removed all the machines from productions. Now, if I show you all the graphs side by side, it's very clear to see that by looking at one specific instance in isolation, we don't really have enough information to understand whether this issue is experienced only by that machine or is experienced by overall cluster. So hopefully, with this, I was able to convince you that there are certain failure modes that we are not able to effectively predict and actually measure by looking at the specific health of one instance in isolation. Instead, we should look at the state of the instance in comparison to the other instances of the cluster. So how can we actually architect a system that then implements this principle, that looks at the health of all instances and compare them among each other? That's how we can implement it. And let me show you how we implement our systems at Fastly. So we got each single host, and each single host has a number of components. Starting with, we implement a daemon, which periodically checks certain metrics over the machines. And the signal collected can be, for example, service error rate, the response time, processor time, CPU load, and so on. We collect these numerical metrics at a fixed time interval, and we take this metric and stream them to a logically centralized location outside of the machine. Then we have all the machines in the cluster doing the same. So each machine collects a number of signals. This signal then gets aggregated into a logically centralized component, which takes the results, which takes all these signals, performs some mathematical computation on them, and decides globally what should be the state of every machine in the cluster. Now, let's focus a bit on this white box, okay? So this white box is some component which takes as an input a multidimensional discrete signal, performs some mathematical computation on it, and outputs another signal, which possibly has got a lower dimensionality and a lower cardinality. Now, if some of you in the audience are familiar with machine learning or with control theory or signal processing, will find this familiar, because this is an abstraction that is common to all these three disciplines. For example, in machine learning, this is what is a classifier. So a classifier is a component which takes as an input a multidimensional signal and categorizes this signal into a categorical variable that describes in a concise way the input. Similarly, in signal processing, there's a similar abstraction. Actually, the filter is the main overall abstraction of signal processing, which is a component which takes as an input a multidimensional signal and outputs a signal which has got a different statistical property. In control theory, there's also an abstraction like this one. So a controller is an abstraction like this one. So a controller is, again, a component which takes an input set of signals, which describes the current state of a system, and outputs a control signal which should influence the state of the system in a future point in time. So I'd like to let this sink into a minute. So as you can see, by architecting the systems the way we did, we were able to abstract a concrete distributed health checking problem into a more general problem, which then can be used using tools and techniques from machine learning, signal processing, and control theory. So we were able to abstract this problem into a classification problem, or a filter design problem, or a stable control problem. Now we are able to use all these tools and techniques to solve our practical distributed health checking problem. Okay, so this is all nice and well, but how do we practically implement a filter which will address this problem and will timely and accurately identify the health of a service? Let's find out. Let me show you an example design on how we can build a system like that. Now, the example that I'm going to show you is a simplified version of the system we built at Fastly. I will start describing how we can decompose a large, complex problem into smaller, more tractable problems. And then I will give you examples of some tools and techniques that we can use to solve each specific sub-problem. Now, I would like to reiterate that this is not the only solution for this specific problem. This is only one solution. But hopefully, the design I will show will probably give you enough inspiration to be able to design a system that might solve your specific constraints and address your specific objectives. So, as I said, at Fastly, the service instance that we want to monitor is a HTTP reverse proxy. We periodically start querying a test endpoint and collect two different metrics, the request error rate and the response time. So we collect these metrics from all the instances running in our cluster, and we take the results of these signals and go through a three-stage filter, which will then determine the health of each specific instance. So the first stage is a denoising stage. The objective of this stage is to take the input signals and remove noise from the signal and only extract the features of the signal that are interesting for us to make our decisions. Second stage, we take the results of this denoising stage. We take these denoise signals, and we feed them together into an anomaly detection stage. The objective of this stage is to compare the various instances and try to identify whether there is some instance that is misbehaving and its behavior deviates from other machines in the instance. Finally, we go through the third and final stage, which is a hysteresis filter. The objective of this hysteresis filter is to stabilize the output, is to ensure that whatever decision we make out of the anomaly detection, the decision is stable and does not fluctuate, because we want to avoid the services flapping in and in out of production. Now, for the sake of clarity, I only show one single instance of the anomaly detection and the hysteresis filter, but in practice, we need to have one instance per host in our infrastructure. So in summary, we got 3 stages: denoising, anomaly detection, and hysteresis filter. And I will go through each of these stages and how we can implement a system that addresses the objective of these stages, starting with the first one, which is the denoising stage. So let me start motivating why do we need denoising in the first place. This is an example of a response time of our HTTP reverse proxy over a period of time. This signal has got some interesting properties. So as you can see in the first half of the graph, the response time is pretty low, is around 0.25 milliseconds. Then something happens towards the middle of the graph that causes a persistent increase in latency from 0.25 to 0.5. And then for the second half of the signal, we have a latency this is pretty much around 0.5 milliseconds. There are also some transient events. As you can see, we got some transient spikes which can occur throughout the signals. So to make decision, we're only interested in the persistent changes in the signal. So we're interested in the fact that it's got a 0.525 millisecond latency at the beginning, that we got a persistent change in the middle, and a 0.5 latencies at the end. We're not really interested in a transient event, because even if we wanted to react on the transient event, by the time we actually reacted, the event has gone away, because it's transient, right? So we want to ensure that we filter out the signals and we remove all the noises. Now, from all the various disciplines, there are a number of tools and techniques that can be used to solve this problem. And I will show you an example on how we can solve this problem using the first one, which is probably the simplest one, and is the moving average. So moving average works as follows. We have our input signal, which is potentially very noisy, and we define a window of samples that is an integer value, and we compute the mean among all the samples within this window. Then, as the signal progresses, we slide the window as new samples come in the signal, and we compute the mean among all the samples within this window. As you can see, the output signal is much, much smoother than the input one. An important configuration parameter is the size of the window. The larger is the window, the more smoother is the output signal. However, at the same time, using larger windows can also cause problems because it will make our filter slow to react. So that's so the size of the window is a good tuning parameter that gives us a trade-off between stability and reactivity. Let's see how this works on the signal that I showed before. Let me show an example of what would be the output signal if we have a window of 20 samples. That would be the result. As you can see, we pretty much got rid of all the spikes that we had in the unfiltered signal. And it's quite fast to react to the persistent change of latency towards the middle of the graph. But you notice that it's a bit noisy still, the output graph. If we increase the window size, the signal gets smoother and smoother and smoother. But as you can see, the larger is the window, the slower it is to react to the increase in latency that we experience toward the middle of the graph. So again, to reiterate, the congestion, the window using the moving average gives a good trade-off between stability and reactivity. Finally, second, we go through an anomaly detection stage. So as I mentioned before, each single host, each single service instance can be represented by 2 variables, the error rate and the response time. So we can plot the results, the state of one specific host as a dot over this plane, where the x-axis represents the response time and the y-axis represents the error rate. So let's plot all the hosts in our cluster over this plane. And the problem that we want to address here is, given a specific host, like this orange dot, we want to understand whether this host is behaving comparably to other hosts in the cluster, or its behavior deviates substantially for all of them. Again, there are a number of techniques from literature which we can use to address this problem. There are many of them. And I'll show you an example on how we can solve this problem using simple thresholding. So that's how we can solve the problem given a simple thresholding. we got these orange dots, and we want to understand if its behavior deviates from all the other gray dots in the plot. So what we do, we compute the mean, error rate, and response time among all the gray dots. That's going to be the result. We then compute the standard deviation across both metrics. So the standard deviation is a scalar value which represents how scattered are points across their mean. The more the points are scattered across their means, the higher is the standard deviation. We then define two thresholds over these two axes that are proportional to the standard deviation. And then let's consider our host to be healthy if it's within this threshold, or unhealthy if it's outside this threshold. Now, this alpha coefficient is a tunable parameter, which gives us a trade-off between reactivity and stability. The greater is the alpha, the more stable the system is, because we need to have a much higher deviation to trigger our service to be unhealthy. But it may also cause our system to be slow to react. So again, we got the usual trade-off of reactivity against stability. Finally, we need to go through a hysteresis filter with the objective of stabilizing the output. Now, in the graph that I showed before, there was actually a problem that I didn't mention. What happens if a host fluctuates quickly over the boundaries of a threshold? Let's suppose that we've got a service that is unhealthy. If it crosses the threshold, then will be considered healthy again. And if it crosses the threshold again, will be considered unhealthy. So if you got a host quickly fluctuating across this threshold, we cause the service to flap and go quickly in and out of production, which is a behavior that is undesirable and we want to avoid. So the objective of the hysteresis filter is to stabilize the output and ensure that whatever decision is made, this decision is stable and does not fluctuate. Again, we can dig into literature for a number of techniques that we can use to solve this problem. And I will show you an example on how we can address this problem using sharp hysteresis. So the idea behind this sharp hysteresis is the following one. Let's define an additional threshold, and let's configure our system to consider a machine to be in production only if it crosses the inner threshold inwards, and remove a machine from production only if it crosses the outer threshold outwards. Then, with this additional threshold, to put a machine back into production is no longer sufficient to cross the inner threshold inwards. We also need to the outer threshold. We also need to cross the inner threshold. Similarly, to remove a machine from production is no longer sufficient to cross the inner threshold, but we also need to cross the outer threshold. So this is, in summary, the system that I was explaining you. So we go through these stages: denoising, anomaly detection, and hysteresis filter. And there are a number of techniques that we can use to implement each of these specific stages. And in particular, I show you the example using the simplest techniques, which are machine moving average, simple thresholding, and sharp hysteresis. Now, I guess you're probably curious to understand if this actually works. Well, let's actually find out. Let's go and revisit the two examples that I showed you earlier on. This is the example of the misbehaving canary that at certain point starts experiencing an increase in response time. Now, as I showed you before, this is a case which we can correctly identify just using a fixed threshold of response time and remove a machine from production if the response time exceeds this threshold. So if you use this filter with the design I just showed you, that would be the threshold. So you can see we are still able to accurately identify the misbehaving instance, but we'll do it in a much quicker way, because we'll be able to understand the misbehavior much earlier than using a fixed threshold. Now let's see actually the second example, the example of all cluster on fire experiencing high load. In this case, as I showed you before, using a fixed threshold will cause a cascading failure because we will remove all machine from production. Instead, if you use the anomaly detection mechanism that I showed in the previous slides, using the same configuration, the same set of parameters for the previous case, that will be the threshold that we need to exceed. So as you can see, in this case, our filter correctly identifies that the issue is generalized to the cluster and does not remove the misbehaving instance from production, but will keep it in production. So I would like then to make a bit of comments on how can we physically implement these things and some interesting implementation details. So as I mentioned before, we got a number of hosts, each host emitting a couple of signals. These signals are then aggregated into a logically centralized filter, which then processes them mathematically and makes a decision on the global state of the cluster. So we decide which specific host should be considered up and which specific host should be considered down. Now, if you want to practically implement this, the filter is going to be a single point of failure. because if a filter is down or is misbehaving, then we cannot identify and determine what is the health of any host in the cluster. And we may want to consider the whole cluster down. So to practically implement this, we need to replicate the filter and have several instances of the filter to coordinate among each other and use, for example, some quorum or some distributed consensus. However, there may be some using distributed consensus seems difficult. Maybe there's a simpler and a better way. So we can actually make an intuition right now. That is, that the output of the filter only depends on the filter implementation and the input. So if you've got several instances of the filters all receiving the same input and being configured in the same way, we necessarily make the same decision. We'll have the same output, right? So what we're going to do, we're going to create several instances of the filter, one instance per host, and we'll feed this filter the same input. All filters will get the same input. Now, you will notice that each filter still makes the decision for all the hosts, but that is no longer necessary, right? Because if you got one filter instance per host, we don't need each filter to make the decision for all the hosts. We can make one filter instance make decision only for one single host. So we can partition the whole decision space, this whole result space, and ensure that one filter instance is responsible only for one exclusive portion of the decision space. Now, after doing this partition, we can actually collocate each filter instance into a host. Now, this design gives us some very interesting properties, because as you can see right now, by implementing the system in this way, we no longer need to have any coordination between filters, among filters. So each filter makes the decision for an exclusive region of the decision space without needing to coordinate or to have a consensus with other filters. And if one filter fails or experiences some misbehavior, all we have to do, so all is going to happen is that the machine, the host on which this filter runs, will start misbehaving. So that gives us a good resiliency without needing any coordination. So this is pretty much the end of my talk. I would like to summarize a bit the main points that I treated in my talk. And the first argument I made is that making health check decision based on the global state of a service is desirable for catching certain failure modes, which will be otherwise unable to check if we only look at specific instances in isolation. Second, by addressing the system, by modeling the health checking systems as a classification or a filter design or a stable control problem, we are then able to exploit techniques from literature of these three disciplines to make to design our health checking systems. And finally, distributing replicas of the health checking processing logic to individual hosts makes it possible to have a resilient design without requiring distributed consensus. So in conclusion, I would like to show you a number of references that you may find useful if you want to go home and build an anomaly detection for health checking system on your own. So I put some references over here. So the first two are typical handbooks for signal processing. These are typical undergraduate textbooks used for signal processing. They're quite heavily mathematical. I think they're probably more Greek characters than actually Latin characters. But they're actually quite rigorous and comprise a very comprehensive overview of the denoising problem and how to remove features, undesirable features from systems. So if you're interested in anomaly detection, I put here a couple of interesting books. So the first one is a typical undergraduate book for machine learning. There are several machine learning books, but I like this one because I like the way it covers the classification problem. While the second problem, but the first one is heavily theoretical, while the second one provides, I think, a very good mix between theory and practice. So it's a bit more high level on the theoretical aspects, but provides some very interesting example and very actionable insights. And finally, if you're interested in the problem of stable control, there are two references that I would suggest. So the first one is a typical handbook that is used in mechanical engineering, electronic engineering undergraduate courses. Again, that's very heavily mathematical, but it's also very rigorous. And the second book, this Feedback Control for Computer Systems, is a very good combination between theory and practice. And I really recommend the book, actually, because they got a number of chapters which provide a number of very useful and very common examples, which I recommend to have a look and might be useful for you for other problems you may face in your work. So that concludes my talk, and I would like to thank you very much for the time and attention, and I'm happy to take any questions you may have. Thank you very much. Could you please come to the mic if you got any questions?
if you're decentralizing your decision-making process about performing this filter, but you still need the data from all the nodes, where do you put the data?
So we use a combination of a multicast and a gossip protocol to distribute the data. So all nodes talk to each other, so they kind of like logically broadcast the data.
How much CPU you spend for signaling processor?
How much, sorry?
CPU you spend for the signaling processor.
How much CPU?
CPU, yes.
Well,
if you have 2,000 hosts which send logs by multicast, it's maybe need 100 hosts for signal processing.
No, so the process is actually very simple. So in the specific example that I show you, which is pretty much what we use in production, uses a moving average. So a moving average is very simple to compute. So you can do it like in a constant time. It's very simple. So even if our clusters are not that big, so we got like tens of hosts, and that's like the order of magnitude number of hosts. So we don't have to process data from different hosts. But I would actually argue that as long as you don't use very complex algorithms, we don't really have much CPU utilization. So I'll probably argue that the CPU utilization that our current daemon is probably maybe 1% is really negligible. So, yeah.
Thank you.
So the signals that you're collecting, are they from the logs, or the time series, or the combination, and what kind of standards do you have, and what kind of learnings you learn from your implementations?
So what we do, we actually have a daemon that periodically checks the information, and so they don't come from logs. So we got this daemon that specifically collects these samples, and then disseminates them using a combination again of multicast and gossip protocol. We also actually save all the results, and we upload them to BigQuery actually. The reason why we actually save all the results is that we can then replay decisions. So if you want to tune filter in future to understand whether if something goes wrong and want to maybe readdress the design, we save every single sample that we get, we save them. So we can kind of resimulate different combination parameters to understand if filters will behave better.
And when you say daemon, is that specific to your implementation that you have wrote in-house, or is it like can be used for any reverse proxy implementation?
No, the daemon we wrote it from scratch ourselves. So that's yeah, but it's not really that complex. So just there's some we implemented it in Go, just some Go routines which periodically check standings and emit them. So.
Is it open sourced or?
No, it is not yet. We're considering open sourcing that, but it's not at the moment. Okay, looks like there are no more questions. I'll be around if you want to ask me any more questions in private. Thank you very much again.